The pleasure to have our first talk by Cesare Tronci from Surrey, who's going to talk to us about hydrodynamic vorticity and helicity of conservative liquid crystal flows. Cesare, please.
Thank you. So, in this talk I will show you some interesting formulas that emerge when one... Is this okay?
They are.
Yeah? Oh. What about now?
Yeah.
Yeah, okay. Thanks. Yeah, some interesting formulas that emerge when one looks for, especially for a helicity conservation of conservative liquid crystal dynamics. In particular for Erickson-Leslie theory, but it can be generalized to other theories such as Landau-de Gennes. So this is joint work with my friend François Guy-Balmat, who was, we were colleagues when we were at EPFL in Lausanne in Switzerland, and we came up with these two papers here in which we kind of had this result of analyzing helicity and vorticity in this context. So yeah, let me get started now. So backflow. We were reading all these papers on liquid crystal experiments, and it was clear that this concept of backflow is well established in the framework of liquid crystal flows. This is a concept that relates velocity, fluid velocity, and the order parameter nematics in liquid crystals. And we were looking for a possible quantity that encodes this interplay between velocity and order parameter nematics. And so we came up with a possible quantity that at least encodes our understanding of what the backflow could be. So if one looks at Erickson-Leslie dynamics, at least for, well, even with dissipation, there is this quantity omega, which is a vorticity quantity, that interestingly enough satisfies a broken, well, how should we call it, broken frozen in condition along the liquid crystal fluid velocity little u. Okay, so in the particular case when dissipation is neglected, as by just studying the mathematical properties, then of course one gets vortex line solutions, because this is frozen in condition, which is well known to allow for vortex line solutions. Now this quantity arises, as I said, in the context of Erickson-Leslie dynamics, but it can be generalized, especially to the Qian and Sheng formulation of Landau-de Gennes theory, dynamic theory. Now, I think it's important, at least to me, to mention that this works regardless of what kind of free energy one is using. Okay, so what is this quantity? How is this constructed? How does it emerge? Okay, I mean, this is, in the dissipationless case, this is a frozen-in vorticity, because it's taken as the curl of something, which is an extended velocity, or I should better say momentum, and J is an inertia constant. Yeah, J is an inertia constant. It's the constant that okay. So yeah, so this is a constant that encodes the inertial properties of the director rotation. Now, of course, one can say that this is not a relevant term because the inertia is usually neglected in liquid crystal dynamics. However, in this context, we are retaining this quantity because, of course, I mean, the talk is about conservative liquid crystal dynamics. If you throw these out, then there is nothing interesting you can say about conservative liquid crystal dynamics. So please allow me to retain these inertial properties of this rotation.
It's just time derivative, not material derivative.
N dot, okay, sorry, you're absolutely right. This is material derivative, yeah, right, sorry.
It is material or it is also co-rotation.
Material.
So you neglect co-rotation.
You just transport by the velocity because it's scalar. No, it's
I think I will show you how this works. You might understand it better in the following discussion because I will show you how this arises. I'm not neglecting the co-rotation term.
So what are the properties of n? Isn't the n is it a covariant or contravariant vector?
No, it's not. It's not. It doesn't. It's just. I mean, you can think of it as a vector on the unit sphere. It's a point on the unit sphere, which I'm describing as a unit
So
vector.
then don't you need to project them on the unit sphere because if I transport it, it's not going to be unit vector?
I will. Yeah, I will. I will do this by saying that if I assume that its modulus is 1 as the initial condition, then it's 1 at the all the
So
remaining.
it just transport. Okay.
Yeah, exactly. Okay, so yeah, the interesting idea was when we saw this quantity is that this couples fluid velocity and ordered parameter. So maybe we thought this could be a quantity that encodes this backflow concept. Now, I think this is even more interesting than the formulas I showed earlier. This is typical type of formula that appears in fluid flows. So it says that when the dissipation is neglected, that there is a circulation quantity that's preserved in time. Now, for Euler flows or compressible flows, this is called Kelvin-Ether theorem. And so this is a circulation that's computed along a loop that moves, an arbitrary loop that moves with the fluid velocity. So, yeah, the omega equation then follows from Stokes' law. And when the dissipation is neglected, this produces conservation of this helicity functional. And then, of course, when one looks for conserved quantities, then one has to look for boundary conditions that ensure that the quantity is indeed conserved. And, well, yeah, anchoring conditions allow for this conservation. But there is also there are also more general boundary conditions that satisfy that.
Could you please do me a favor and show how the omega equation follows from Stokes' law?
Okay, well. So you take, I shouldn't have said omega, I should have said the helicity.
No. I'm saying that the omega equation follows from Stokes' law.
Yeah, that's probably too simple. So the omega equation, so if you just look for the dynamics of this circulation quantity, okay, you just computed the time derivative of that circulation quantity, you apply the exterior differential to that, you take the curl of that equation, and then you get the omega equation.
Okay. I'm just trying to elucidate so the Stokes' law for an integral around the loop that
Yeah.
that
Takes you to the surface integral of the
Yeah, yeah.
differential.
So that's equal to the surface integral of that omega. Exactly. The
Yeah.
surface
Yeah.
integral.
Oh, yeah. Okay. Yeah.
And then d by dt of that, all the, integrated over a surface, vanishing gives your previous formula.
Yeah. Yeah.
Show the previous.
Yeah. Well, I mean, it gives me my previous formula integrated.
Yeah.
Yeah.
Around an arbitrary loop.
Yeah.
Yeah, just show the previous formula. Yeah, it gives that one. Right? So it's,
Yeah. Integrated over the surface.
yeah, so the mystery of that is there's no mystery.
No, there is no mystery.
The Stokes law.
Yeah. 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 Well. Okay. Okay. Yeah. So boundary conditions, are you already commented on that? Okay, so now question, what's going on here? How do I just show you these formulas? How do I get these formulas? Well, if we really want to be honest, one probably could say that we didn't do much besides reading carefully these guys' works. Volovic and Erringen, especially Volovic, established the first of my knowledge connection between Erickson-Leslie dynamical theory and the Hamiltonian theory of Young-Mills fluids. In particular, he showed that the angular momentum of Erickson-Leslie dynamics can be interpreted as a Young-Mills charge of some type of Young-Mills fluid. On the other hand, this other guy, Erringen, he was not really aware that he was doing Young-Mills fluids, but he was. And he came up with something that he called Reines tensor, and turns out to be exactly a Young-Mills magnetic vector potential. Okay, and in the particular case of Erickson-Leslie theory, the expression he wrote was nabla n cross n. Okay, so at this point, Young-Mills fluids is basically plasmas. Okay, plasmas are fluids that carry an electromagnetic charge. However, now these are Young-Mills fluids, so the charge is not electromagnetic, but it's some kind of non-abelian Lie algebra quantity. Okay, so we know from the theory, the mechanics of charged particles, that there are two types of momenta. There is the kinematic momentum and there is the canonical momentum. So we can go from one to the other. And of course, if we want to develop a Hamiltonian theory, we would better look at the canonical momentum.
What is a gauge field here?
Gauge field, so it's this thing. This is the magnetic potential of a Young-Mills field.
But gauge field implies local invariance of local changes of the parameter.
Yeah, no, so this thing is not gauge invariant.
So it's not gauge invariant. So
It's not gauge invariant.
Young-Mills, it is not gauge field.
No, it's a variant of Young-Mills. It's a variant of Young-Mills that encodes for the symmetry breaking that arises from the existence of the preferred direction in space that's encoded in the director. So it's a variant of, and this is
a variant of Young-Mills because it is essential for Young-Mills. It is essential that there is a gauge invariance.
So this is a variant.
No gauge invariance. It is not Young-Mills.
Okay. So this is a variant in the same sense as Volovic's work. Okay. So if you go through Volovic's work, it's clear that he's starting with Young-Mills fluids, and for example, he develops the theory. He develops his theory of spin glass or spin waves, and then he extends his theory to nematic order parameter, and he ends up with this variant. Okay, so when I say Young-Mills fluid, I mean Volovic's formulation of Erickson-Leslie theory. Okay, so if you really want to be strict, probably I should say Volovic's theory of Yang-Mills variant, fluid variant. However, whatever it is, I will show you what I mean by all this.
Just
But-
couldn't we say that the gauge symmetry that's broken is SO3?
Yes.
Isn't that the answer to Lynn's question?
No, because he probably means that if you break that symmetry, then it's not a Yang-Mills fluid.
No, the Yang-Mills fluids have broken symmetry. Right, Lynn?
Is that, I mean, what's
Yang-Mills fluids have broken symmetry.
Yes, it is broken symmetry, but
That's
there
where
is
the
local,
the local?
gauge
Yeah.
invariance.
That's the
This is
SO3.
an electromagnetic field and all other gauge fields.
Yeah, so luckily it's SO3.
It
And
is
the
it is
quantity
essential.
A-
It is like a difference between superfluid and superconductor.
Well, it will be written for a particular gauge, I think.
No, there is no
There's-
there is no gauge freedom here.
From the start, it's not gauge symmetric. It's the same as you mentioned.
Actually,
No.
there is a gauge freedom. It's a freedom of the invariance of the Lagrangian. And then the Lagrangian is invariant under local rotations.
Local, not local.
Local.
Global. On the global. On the global. rotation.
Well, this
It's
is
invariant under global rotations, right?
And it is a great difference, of course. Global
No,
rotations, yes. Local rotations, no.
yeah, but I mean there is something. I mean there is something going on here. I mean the local SO3 symmetry is broken by the director. So strictly speaking, it's not a Yang-Mills fluid because of the existence of a symmetry breaking parameter. Okay, so this is an extended version of Yang-Mills fluids that carries with it the symmetry breaking parameter. However, let me say that things work rather well anyway, even if you keep track of the order parameter dynamics. Okay, I will show you how this works. And I mean, it's not that I will show you how this works in, for example, in the Euler-Poincaré framework, but it's all written in Volovic's work. Okay, so this takes us to the question of what about Yang-Mills fluids? Of course, there is a lot of geometry involved in it, and because I mean, as far as I can tell, I could stop here. I say this is the vorticity, this is the helicity. This comes from the canonical definition of momentum for Yang-Mills fluids, and there is nothing else to be said. However, there is a huge mathematics that's behind it, and it probably also arises from Lenz's question. And so let's try to understand what's going on. So why, and what do geometry and liquid crystals have in common? So the main idea from reduction theory is that, for example, in fluids, Lagrangian trajectories evolve on a manifold, while Eulerian variables take the system to the tangent vector of this manifold. Actually, there is more to it because the manifold is a Lie group, which is the relabeling group. We know that fluid flows are relabel invariant. And for example, the fluid relabeling works so that the initial condition is taken to the current position by the diffeomorphism gamma. And tangent space is actually spatial because this is the tangent space at the identity of the group. And the reason why it's spatial because the tangent space is the Lie algebra, which is then endowed with the commutator operation. Okay, so this is just to illustrate the setting in which we are working. Okay, so Lagrangian variables Lie group, Eulerian variables Lie algebra. So I will try to be quick. So the plan is to first add the gauge group to the relabeling symmetry, which otherwise would take us to just Euler's equation. Then, and this is related to Lenz's question, we will break the gauge group, which is what happens for nematic liquid crystals. And after that, I will show you how this our interpretation of backflow is related to a momentum map. And I will try to give an idea of what the momentum map is in this framework. Okay, so let's try to understand how a fluid with internal symmetry works. So for now, I'm not breaking the gauge symmetry. I'm just adding the gauge symmetry, but I'm not breaking it, okay? And I'm not even inserting any fields, just the simplest possible case. Okay, so we have a fluid with spin density sigma. This takes values in the, well, dual Lie algebra of SU2, which is isomorphic to SO3, but the most important thing is that we will work on R3. And if we work on a Lie algebra, then we have to write down what the commutator is. The commutator in R3 is simply the cross product. So the bracket of A and B is the cross product of A and B. So then the simplest conservative fluid system is, for example, of this type, in which F is some interaction potential that eventually carries an external field. And now we want to ask how is sigma defined and what's the geometry behind this, okay? So we go back to our picture. We had diffeomorphisms in the previous picture, but now we add another thing, okay? We add this thing, which is mappings from physical space into SO3, which is just the gauge group, which accounts for the particle rotational state. Now the assumption, because we are studying systems with symmetry, is that the Lagrangian is G-symmetric. G-symmetric means gauge invariant and diffeomorphism invariant. Okay, so this is for the Lagrangian trajectories. Now what about the Eulerian variables? The Eulerian variables are the fluid velocity and the angular frequency omega, which takes values in the Lie algebra of the gauge group, okay, which is identified with R3. Now, how does sigma emerge? Sigma is the conjugate momentum which is associated to the angular frequency omega. So it appears when you move from the Lagrangian picture to the Hamiltonian picture, which is actually what Volovic did. And we will come back to this. Okay, so let's see how this works. Okay, we have our Lagrangian, which is defined on our generalized Q and Q dots. Okay, so we have eta and R, and we have eta dot and R dot. These are the Lagrangian fluid paths, and this is the orientational state of the molecule. Now, of course, I know that this Lagrangian will give me Euler-Lagrange equations on G. However, I don't want to study Euler-Lagrange equations on such a complicated group. Also, I want to have the Eulerian picture of my system. Okay, so how do I get the Eulerian picture? By symmetry. First, I introduce the symmetry, the gauge symmetry, and I introduce this quantity R dot R minus 1, and by the usual isomorphism between SO3 and R3, I can say that this is nothing else than my angular frequency omega bar in the Lagrangian frame, okay? Now, since I said I wanted to have my theory in the Eulerian frame, how do I get to the Eulerian frame? I compose with eta minus 1, because I know that eta governs my Lagrangian path, so in order to get to the Eulerian frame, I have to compose with eta minus 1, and this is what I do. I know that my Lagrangian has a relabeling symmetry, so I compose with eta minus 1, and I compose everything, eta dot and omega bar, okay? So eventually I get my Lagrangian, which is only a function of u and omega. Now, how do I get the equations of motion? Well, I know in mechanics that there is Hamilton's principle, okay? So I just apply Hamilton's principle and I get my equations of motion. Now, okay, one thing I would like to mention, this is far from being easy. Now, this is the short version of it. This belongs to a whole big theory which is called reduction by stages, and it's reported in the work by Sendra, Marsden, and Ratio, okay, 2011. sorry, 2001. So Hamilton's principle, get the equations of motion. Equations of motion are written like this. So when I say sigma is the conjugate variable to omega, sigma is exactly the dl d omega, okay? And d by dt denotes material derivative. I study incompressible flows for simplicity, but I can also do compressible. Now, this is the framework in which I'm working, and this is how you derive an Eulerian model starting from the Lagrangian picture by applying reduction by symmetry. Okay? So, now, let's get to the point, because we want to do liquid crystal, so we have to break the symmetry. Which symmetry? The gauge symmetry, which means this symmetry arising from this group of mappings from the fluid domain to SO3. Okay? So, at the beginning, I will just concentrate it on the case of rod-like molecules, but as I said, we can extend the whole treatment to Landau-de Gennes and conformation tensor order parameter. Okay, so for this case, symmetry breaking is encoded in an extra parameter, and for the case of rod-like molecules, this is encoded in an unsigned unit vector, which is called director. And the role, the main role at the initial time of this director is that it appears as a parameter in my Lagrangian, in particular in my potential energy, as it always happens in symmetry breaking. Okay, so I have my new Lagrangian, which is formally as a mapping the same as before, but now depends on a parameter which is n0. Of course, I have symmetry breaking, which means that I cannot just do the same operation as before, okay, because the gauge symmetry is broken. However, I can let my group, my gauge group, act on the order parameter and enlarge the domain of my Lagrangian in order to comprise the director space, the order parameter space. Okay, so I let my Lagrangian depend also on my order parameter space. And this is how the symmetry breaking appears in this context. For the rest, it's like I did before. I'm just including another variable, and I'm letting my group act on this variable. Okay, now, so far, it's interesting to notice that this step here, this is exactly the same process that's involved in the reduction of the dynamics of the heavy top. Okay, so a heavy top, it is a rigid body subject to gravity that rotates on a plane with a fixed point, and it's pretty well studied, and we know so many things about the heavy top. Okay.
You mean that in that case, the gravity is the same as at naught?
Is the same as?
At naught.
Let's refer direction.
Yeah, exactly. That's the vertical axis.
So you are assuming uniformity of n naught in your theory.
No. No. I mean, if you assume uniformity, it's exactly like that. If it's not, you can still say, I mean, from the purely geometric viewpoint, is exactly the same. Now, of course, you have gradients in your Lagrangian, okay, and this is what gives you non-uniformity. But from the reduction, because you say that your Lagrangian depends on n, not on the gradient on n. So the dependence on the gradients on n is implicit. So it doesn't really affect the treatment. Okay, so now, because we are still in the Lagrangian frame, we want to apply the recipe and get to the Eulerian frame. So we compose with eta minus 1. Compose with eta minus 1, and we get a Lagrangian which depends on the Eulerian fluid velocity, the Eulerian angular frequency of the director, and the director itself. What do we get? We get Morally, the same equations as before, but now we have extra terms that arise from this order parameter. Now, there is a force term that appears in the momentum balance equation. There is a torque that appears in the angular momentum equation. And there is my director evolution equation. Yes, I was expecting this.
I was refraining for a while, but now I'm going to start to say. These are PDEs, and at some point you have to worry about derivatives. And this is the first time I worry, because you see the gradient of n. The gradient of n sees the gradient of omega. The gradient of omega sees already two derivatives of u. Is this equation locally well posed?
Nobody knows that. This is a
Locally well posed. I'm not talking about all the other equations could have blown up at time 1, but at least for a short time, until now, you have the local existence because you didn't have the problem of highest derivative in the velocity equation being of vectorial form with an unknown sign, which is what happens now when you see a gradient n, which is essentially a gradient of omega, which is two derivatives of u. Okay?
Yeah.
All right.
Yeah, this is something certainly to worry about.
So, big time, because we can write beautiful equations, but if they don't have solutions, maybe we shouldn't. Okay? So, I've
But
said.
we don't know they don't have solutions.
That's right. So we can talk about it, but I think it would be time to know that they have solutions. So I think that one of the interesting things here is, if you go back to your Lagrangian, ways to either cure this possible ill-posedness, the fact that you might have anti-diffusion, okay, backward heat equation. That's what I'm talking about. I'm not talking about that the thing becomes infinite in finite time. That's not the issue. The issue is that you cannot, that the smallest, the highest frequencies move fastest, okay? So in order to avoid that, you might have, because the equations are so nice, you might have some beautiful miracle in which that is prevented from the equations. And that's what I'm suggesting. That is something that you need to look at. If not, then you have to add some cure. The cure will be dissipative, something in or new physics that implies the cure.
Yeah. Yeah, so, well, what I'm going to do is actually to specify the Lagrangian and get to something which is pretty well known.
Okay.
So this is, I mean, I don't know, under which conditions I can write these equations, to be honest, I don't know.
No, okay, so let's go on, that I think that the Lagrangian is not what I'm worried about already, unless the L, not right.
Well, this is the Lagrangian.
Okay.
Okay.
So it's an F there. So you see here. Okay.
Okay, so Lagrangian is kinetic fluid energy, rotational energy, and free energy written as the Frank energy. I'm neglecting surface terms, but I could also introduce them. Now, this gets me to the Erickson-Leslie equations. Okay, the way I do this is I insert, where is it? I take this equation, I rearrange these equations that I can use this equation and insert back these into these and get my Erickson-Leslie equation. Okay, now this is well known in the presence of dissipation. In the absence of dissipation, I wouldn't know. The interesting thing about this system, at least from a geometric viewpoint, is that the projection of the angular momentum along the director is not just zero at the initial time and preserved to be zero. It's zero, identically zero at all times. And it's seen by this relation here. And I like this because this really reflects the fact that these rods don't care about rotations about the director itself. Okay, so I thought this was an interesting remark. Now there is a lot of more mathematics to it. What I explained you today is called Euler-Poincaré reduction theory. There is a whole counterpart to this, which is called Lagrange-Poincaré. It's well, I think personally it's much more difficult because you have to really compute connections and curvatures to develop the other side, but eventually this is what you end up with. It's a whole jungle, okay? You can do Euler-Poincaré reduction, you can do Lagrange-Poincaré reduction, and eventually the two reductions are compatible and you can exchange from one to the other. You can pass from one to the other at any step. However, now the question is, why do we do all this? What do we get from this? Well, we get the subject, I mean the first two slides of this talk, because we get the helicity of pneumatic liquid crystals. How do we get this? Well, we get it by, again, once more, following Volovic's work. Volovic's work was on the Hamiltonian side, and so let's move to the Hamiltonian side. We introduced the canonical fluid momentum and the canonical angular momentum, and we define the Hamiltonian functional and use Volovic's Poisson brackets. Okay? This simply gives me the Hamiltonian formulation of conservative Ericsson-Leslie dynamics. This is all written in Volovic's paper. Okay? Now, at this point, there is a general theorem that says that if these things work well, then there is a transformation that takes me to the expression of the helicity invariant, which becomes not just a conservation occurring by chance, but it becomes a Casimir invariant of Volovic's Poisson bracket. Okay? Now, this is much more than just say this is conserved. This is a Casimir invariant, and even more than that, it comes from conservation of the Kelvin circulation quantity. And this is the formula that we used. Okay, we just, in order to get the old formula, we just compute the sigma from the expression of the Lagrange. Now, I promised you I would tell something about momentum maps, and here we go. This quantity here is a momentum map. Now, what is a momentum map? A momentum map is a fundamental object in the geometry of Hamiltonian systems with symmetry. It's a generalization of Nether's theorem. Whenever you have a system with symmetry, there is a quantity that's associated to that symmetry which gives you Nether's conserved quantity in the Hamiltonian framework. Using this momentum map in this context gives me the vorticity equation that I showed you already. Okay? What is a momentum map? Can we give an idea of what the momentum map is? Now, I will say you what my idea is, and then maybe Daryl and Tudor may agree or disagree. It's a kind of generating function that is associated to the canonical transformation that's generated by the symmetry group of the system under consideration. Okay. Take a system, take a Hamiltonian system, and take its symmetry. Okay, suppose that it's a Hamiltonian system with symmetry. This symmetry generates a set of canonical transformations that have some generating function. This generating function is the momentum map, which is, in this case, it's written in this way. And there is a systematic, there is a definition that takes from here to here. Okay, now what's what's the symmetry? I mean, what's my system? The system is Erickson-Leslie. What's my symmetry? Symmetry is the relabeling symmetry. Okay, now how do I generate the canonical transformations associated to the relabeling symmetry via this momentum map? Now, it's also interesting to me that if we have a frozen-in condition in 3D projected in 2D, we all know very well, gives us point vortices. Notice that contrarily to Euler's case, in order to solve for this point vortex dynamics, we have to solve the flawless, we have to solve Erickson-Leslie first, and then we have to solve the equations for the director dynamics, and then stick them inside these x and y in order to get the full evolution of these point vortices. I don't know if these point vortices are related at all to defects. I really don't know. So now, what can we say about other molecule shapes? Well, as I already anticipated, we can say again something. Okay, so we define an inertial-like tensor, which for rod-like molecules is defined like this, and we write down the Landau-Gen free energy or whatever energy we want, because as I already said, this approach works regardless of what free energy one uses. Okay, so in the particular case of Landau-Gen theory, we found that the Qian and Cheng model allows for a nice Euler-Poincaré formulation, and so we decided to look at that model. Okay, so this is the conservative Qian and Cheng model, in which a Lagrange multiplier keeps track of the traceless condition for Q, and again, we can repeat exactly the same approach and end up with a helicity conservation for this conservative model. Okay, and the P is the conjugate momentum to Q, which is defined like this. Again, I have a frozen-in condition for the vorticity. So okay, I guess conclusions are listed here, but I guess the most important conclusion is that, well, our understanding, okay, of what backflow is arises from conservation of the total circulation, which couples velocity and order parameter, thereby implying backflow. And I stop here.
Comments, questions, complaints?
So about this helicity conservation law, right? You get helicity for any of these conservative theories you choose, right? Landau-Gen.
There is one that escapes so far. So, well, two. Landau-Gen has been written in the Beris and Edwards formulation, Qian and Cheng formulation, and Volovic's formulation. Right now, Qian and Cheng is the only one that works. We are pretty confident that Volovic's formulation also works. I'm not sure about the Beris and Edwards formulation.
Yeah. Okay. So the point is that this conservation of the helicity is independent of what Hamiltonian you choose, or even, you know, what. It's independent of that. It's even independent of what representation of the order parameter you choose. So all that's left is to ask what happens when you turn on dissipation.
Yeah. when you turn on dissipation, the only thing I could think of so far is that this frozening condition is broken, and then we already know from Euler's flows or plasma reconnection problems that vortex lines may evolve and reconnect, thereby releasing a large amount of energy, for example, in the case of solar flares. And so then one can expect these vortex lines to collide and reconnect. However, I'm not, I mean, this is just an idea, but I cannot be more precise than this.
So these vortex lines are vortex lines of this big omega,
Yes.
the total vorticity. If for some reason you could say my medium is not moving, right, and I don't have any backflow, or because the backflow is negligible, or something like that, can you imagine that just the remaining part of the capital omega could...
Well, in the ideal case, yes, because if the Kelvin ether quantity is preserved along the flow, then orientational motion switches on the fluid flow.
Yeah.
Okay, so in the ideal case, in the presence of dissipation, other things can happen. I don't know.
I was just wondering whether this kind of effect, like you say, like magnetic reconnection, which could release a lot of energy, might still happen if you were in a situation where the velocity was very low. I don't know. Like, it looks like now, at this point, what you get from the including backflow is some additional phenomenon. Like, when you include the backflow and the dissipation, then you get reconnection, right? And the reconnection, could be a measurable thing, couldn't it?
Possibly. Yes. Yeah. But, this is in 3D.
Oh,
And
right.
yeah, in 3D, I don't know what kind of experiments it's feasible to get. I don't know. I don't know really.
Are there 3D experiments in liquid crystals? Yes or no? Anybody?
Yes. Okay. It's good news.
Okay, thanks, Cesare.